Good afternoon, everyone. It is my pleasure to talk about our work submitted in ValueTools 2022 on wind turbine power output prediction. This is part of a larger set of work done together with various collaborators on how to integrate learning and decision making. In the particular work submitted to ValueTools, the work is jointly done with Sandor Kolumban and Nazanin Nooraee. But the larger set of work also includes other collaborators such as Alessandro Di Bucanico and Colin Trent. Without any further ado, let me dive directly into the line of work. So the goal of this work is, given a trove of data, to decide on when exactly should we do preventive maintenance. The setting that we're interested in is inspired by wind turbines and in particular wind turbine data monitoring. In this line of work, typically no failure data is available. What happens is that those wind turbines are equipped with multiple sensors. Those sensors submit the information real time, and the information is aggregated on 10 minutes. And a decision maker needs to make a decision whether they would like to intervene proactively and restore the condition of a component. According to discussions with engineers, what we were told is that the power output of a wind turbine is an excellent predictor for the state in terms of health of the entire wind turbine. We analyzed the data that we look and then that we had from the wind turbine industry, and what we notice is that there is a theoretical model, very well known model, on how the power output is supposed to work as a function of the wind speed. So as the wind increases, and our data set covers wind speeds in terms of meters per second starting from 0 all the way to 30 meters per second, then what we notice is that if the wind is too low, there is no power output. If the wind is too high, and the too high depends on the specifications of the wind turbine, then you can achieve the maximum power output according to the particular aspects of this wind turbine. And in the middle, it behaves like a cubic logistic function. So the objective here is using the data set that we had, and admittedly we had a magnificent data set, extremely dense, that we could analyze to have optimal predictions. We would like to create a prediction model. Such a prediction model would have the following form. So we would like to compute a stochastic process for the power output P over time, T, which is a function of the wind speed, plus there is some notion of an error. And for that perspective, we had multiple physical models that had precisely this cubic law. We modeled the data, we analyzed the correctness of the models, we added a layer to capture the time dependency, because wind has a time dependency, and we validated the model. In the paper, we actually propose a plethora of models, almost leading to an embarrassment of choice. However, my favorite model, and this is the one I'm presenting here, this model is the logistic model. So the logistic model is a very simplistic model that actually tries to precisely mimic the behavior that we see, the flat part prior to the 5 meters per second, the flat part above the 12 point something meters per second, and also the cubic part that we see in between. And as I said, we had a plethora of models, and in the paper we go more into details analyzing precisely the characteristics of these models. But there was one essential element we would like to achieve, and what the element we would like to achieve is that we wanted those residuals to be normally distributed. The reason behind wanting those residuals to be normally distributed is that once we have such residuals, and the logistic model that I presented before has this pattern, the residuals are normally distributed, then what we can do is we can compute the difference between what is actually the power output minus what was our prediction. This is based on the residuals, and of course we need to rescale the residuals according to the volatility. And if that difference, what was actually measured minus what was predicted, is extremely big, then that is an indication that something is not working out. And that is precisely modeling what the field service engineers were telling us, that if the power output is very far from this predicted curve, then something's happening. It could be a malfunction of the sensor, it could be a wrong calibration, but it could also reveal a biggest problem in the wind turbine. So the idea that we had then was actually to extend all the notions from statistical process control to now cover for precisely this Gaussian. But this is now what makes it a little bit of a twist from the general statistical process control. In statistical process control, it is assumed that the normal distribution is actually nothing else than IID samples from a normal distribution. But what we have here is a layer of time dependency, and we have also a volatility that depends on time. So we had to basically extend the ideas of statistical process control to cover a Brownian motion. I'm going to refer to it as a Brownian motion, actually a stochastic process which has a Gaussian element, with a Bayes learning for the time-dependent drift and for the time-dependent volatility. And then what we needed to do is derive what are the normal operation bounds. So what is considered to be that I'm here relatively close to my predicted curve or very far from the predicted curve based on those residuals. So the model that we produced is actually, this is the model of the residuals, and then this model behaves like a Brownian motion, like an extended Brownian motion, and what we learn are precisely these bounds. The moment that you cross these bounds, and notice that these bounds are time dependent, because as time progresses we learn more about the underlying drift and volatility of this Brownian motion, then as we learn that information, the moment that we exit those bounds, then what would happen is we need to do preventive maintenance. And of course we can exit those bounds from both above or below, because the Brownian motion can also develop a negative drift. So in practice we look at a folded Brownian motion, so a Brownian motion with a drift, and we would like in a Bayesian fashion to derive precisely these thresholds that indicate when the field service engineer should intervene. So typically what happens in this context of starting from the data and then predicting a statistical model, then once someone is interested in making a decision, in this context we have the decision of maintenance, then those are treated as sequential steps. So we start with the data, from the data we estimate the statistical model, and then we proceed with the optimization. However, what we would like to do here is integrate both the learning of the statistical model and the cost optimal decision, and what we have noticed is that we don't have a single item, but we have a population of components that share one common characteristic. The structural properties of the underlying stochastic process is exactly the same. So I can say that my stochastic process is a Poisson process or a compound Poisson process. This is what we see from the data. Or in the case that I'm going to be discussing, is a reflected Brownian motion with an unknown drift and an unknown volatility. But what happens is that as we are given the data, before even failure happens, then we notice that for that particular path, the estimation of the unknown drift and the estimation of the unknown volatility differs from one component to the other component. And that, in the context of the wind turbines, might be due to either design differences, installation of different components, a different calibration of the system, or simply a different location in the geography of our wind park. So from that perspective, we would like to create a heterogeneous population individual model that is based on this learning simultaneously of the statistical model and making the decision. So we have this notion of the integrated learning and optimization. So we would like to make this tailored optimization for the objective of maintenance decision making on individual level for heterogeneous components, and the rule that we will have at the end is that the absolute value of those residuals, once it exceeds a certain threshold, which we are to learn, and here this threshold depends on time, so those were the lines that were going downward, then we need to do preventive maintenance. And as soon as it extends beyond that value, so it crosses a value which we denote here by xi, then that is already the value we need also to learn in parallel that indicates the corrective maintenance. For the line of work I'm presenting here, we assume that we know this psi value, and we're only interested in learning the drift and the volatility of the reflected Brownian motion. In order to compare how well our integrated learning and optimization decision-making model behaves, we compare it to different policies. We compare it to a naive offline policy, where we basically use the historical data pulled all together, ignoring heterogeneity. We compare it to the naive online learning, but then what we only do is, for example, if we assume that our drift is constant, we learn the drift from the sample path, and instead of doing a Bayesian updating, we just substitute wherever is the value for the drift based on the maximum likelihood value. And then we optimize with no integration at all. And we also have the Bayes model, which I'm going to be talking in more detail about. So in the traditional setting, what we have is, if we're given some stochastic process, for example, here the reflected Brownian motion, then, and if everything is known, the policy is just a straight line. However, once we go into the setting of the Bayes learning of the underlying parameters, here denoted in a vector theta, then every time we get a new data point, and here the every time is indicated at this point, at this point, at this point, then what we do is we update our notion of that threshold, and that leads to a time-dependent threshold, and that was the delta t threshold that I was talking before. So we have now an underlying stochastic model, which is here a Brownian motion, a reflected Brownian motion with some drift and some volatility. We consider that the drift is independent of time, mu, unknown. We assume that the volatility is of the form sigma square root of t, where sigma is unknown, and w of t is just a Wiener process, scaled 0,1 Wiener process. And we would like to learn the mu and the sigma while reaching the optimal decision, where there are costs depending on the state. We denote the cost for preventive maintenance as Cp of function of the state x, and the preventive replacement costs are smaller are smaller always for every x than the corrective replacement cost. Also, the other decision that we have is a decision of doing nothing, but that also comes with some cost L of x, where those costs depends on the state, and you can view this cost as nothing else than the operational cost at state x. And of course, the question that we would like to answer is, what is the optimal preventive replacement policy? So we assume here for the Bayesian learning that mu is normally distributed, and it is updated according to a Bayesian prior to posterior rule. We can also similarly to that assume that sigma is normally distributed, and again updated according to a Bayesian prior to posterior rule. If we have information on the coupling of mu and sigma, we can consider a joint normal distribution, but if we don't have any information, consider them disjoint. Well, in the first already updating, based on the fact that we use the same data set and the same sample path, those will become coupled, so then there is no expense in just starting with two independent normally distributions for both the drift and the volatility. So here we had this entire vector, and here I'm just going to focus on if we only know the sigma and we learn the mu. However, in our work, we also consider that we don't know both the mu and the sigma, and then under the total discounted cost criterion, we would like to determine the optimal policy by defining nothing else than the total expected discounted cost, which we denote here by V of x comma t. X is the state of my stochastic process, that reflected Brownian motion. T is the time, and theta of t is the information that we have on the mu and the sigma. So basically, for those, if we assume the normal distribution, I just need to know at time t and given condition x what is precisely the mean and the variance of that normal distribution. Notice that every time I'm updating, due to the linearity of the prior to posterior updating of the Brownian motion, the only level of information that I actually need is my state x and my time t, and based on that I can precisely learn what would be theta of t, and theta of t here relies only on the efficient statistic, and that is the linear. So our approach is a very classical approach. We write down the Bellman equations, and for the optimal policy, that leads to an update-dependent control limit policy, or otherwise a time-dependent control policy. The Bellman equations basically indicate that if your state has exceeded the failure threshold, then you need to do corrective maintenance, and that costs C of C. And then with one period later, then you need to discount, and then you start in a new state, which is some random state. Or if you are in a state that has not failed, then you pay Cp of x, and then one state later, then you are in a state of as good as new plus this period of time that has lapsed, so that leads you to a state x of 1. Or if you decide to do nothing, then you pay this delta of and I notice here a mistake in my slides, I'm sorry for that. So here there should be a delta plus then the discounted expected cost in the next state, given that you're currently in state x. So we solve these Bellman equations, and then we show in our theorem that precisely the optimal control policy is a bandwidth policy. And the notion here of the bandwidth policy is that it has exactly this stepwise lines that we showed before. The advantage of this stepwise band policy is that, first of all, it's simple to use in practice, it's easily interpretable, and doesn't suffer from a black box interpretation, but it is transparent, and it, since you already know the structure can be exploited for computational efficiency. So this would be the form of the policy that we have, and as I mentioned before, we wanted to compare it with how it would do, and actually already the comparison between our Bayes model and an oracle model, that you basically know precisely what are the underlying parameters, revealed that the Bayes model is better than the myopic updating cost regret model. It is better than the historical model where we basically pull all the data together and we learn, and it only is worse than the oracle model by 2% on average. So we tried a test bed of several cases to see what would be the most extreme situations that we could find, and actually the most extreme situation is when you have very high volatility and you try to learn it, but somehow you don't manage to learn it very well, and then you misspecify it, and that leads even to an regret, so you're off by a percentage of 2.86, and on average the regret that we computed is 2.07. With that, I would like to conclude my presentation, and I am open to receiving any questions from the audience. Thank you very much.